Hello and good day everyone. In today's video, we would now be discussing about the analysis and design of shear reinforcements for reinforced concrete beams as per NSCP 2015 and ACI 318-14M. Okay, so as a review, what is shear in the first place? When we say shear or shear stress is actually the stress induced by an internal force which is parallel to the cross-sectional area that you are analyzing. So suppose that this is one beam. So again, this is just a review from your mechanics of deformable body subject. So in this particular beam, I would now apply, let's say, a transverse load onto it. So this is now our transverse load. When we say transverse load, it is now the load that is acting perpendicular to our longitudinal axis. So again, this is transverse and this is longitudinal. Okay, so let me just erase those two. Okay, so suppose that this is now our loadings, and let's say that I want to know the shear stress induced about this point. So what I would be doing is that I would be cutting a particular section here. So just like in method of section, so I would be cutting that section. And for you to better visualize, what I would want to emphasize here is that upon cutting our section there, so I would further cut our section in this manner. So paghiwalayin ko po. So that is now our cut section, and let's say that the beam on the right or the section on the right, I will be rotating it in a manner that, or in such a way that you would now see its cross-sectional area. So let's say that this is now the cross-sectional area, and due to this loads here, it would now have a reaction, and that is now, or that particular reaction is now our V at that particular point. So in order for us to get this particular stress, or to get the stress about that cross-section, the shear stress is equal to the force divided by the area, and take note that this area must be parallel. So let me just change my pen color in order for you to see. So take note that this area here must be parallel with your force. Okay, so from that is now equal to, or let me go back here. So that is equal to V over A. So this is now shear stress. Okay, so moving forward, so what is now its connection in the design of reinforced concrete structure? So in the previous video lectures, or in our previous lectures, we have designed our beams in such a way that it would not fail due to bending. So in the previous lectures, you have learned of the terms tension control, compression control, transition, and the like. And from that, you have actually designed for the longitudinal bars, for the main bars. Okay, so during those times, we did not even consider if it would fail in shear. So that is now, that will now be discussed this time. So ngayon po, ang i-take into consideration natin is yung lakas po niya sa shear naman. And as you know guys, that for our beams, or for the beams that we will be analyzing, most of them will now be subjected with transverse loads. So when we say transverse loads, once again, parallel po siya doon po sa cross-sectional element natin or ng beam natin. Okay, so from that guys, so again, before, you have solved for the moment diagrams, then compared it with the strength. This time, instead of us making use of the moment diagram, we would now be making use of the shear diagram. So in order for you to be successful in this subject, you must first master mechanics of deformable bodies, specifically shear shear diagrams. Okay, so again, as discussed a while ago, that our cross-sectional area must be parallel with your force. However, due to various experiments, if we would be applying shear stresses onto our beams, according to experiments, its manner of failure is not entirely perpendicular, meaning guys, hindi naman po ganito yung failure niya. So hindi po straight line yung failure niya, so it is not really parallel for its manner of failure. Rather, it would now look like the one you are seeing on your screens. So it would now be slanted in this manner. Okay, so that is now the shear failure plane of our reinforced concrete beams. Okay, so how can we now prevent that from happening? So we would now be adding shear reinforcement. So when we say reinforcement, in our lecture, bakal, maglalagay po tayo ng bakal, or we would now be putting steel. So in what manner? So our shear reinforcement would now be, once again, transverse. Meaning by transverse, it is now oriented in this manner. So as you can see in our figure on your screens, we have these green lines here. These green lines are now our shear reinforcement. So going back to our previous slide, in order for us to prevent this failure from happening, we will now be applying steel members, or we will now be putting steel members in this manner. Okay, so there. So if you want to look, or if you want to see what it typically looks like, it actually typically looks like this. So for beams, as you can see, that these are now our transverse steel members. So these are now our shear reinforcement, and we call that stirrups. So for stirrups, that is for beams. And suppose that you are designing the shear reinforcement for columns, that is now called ties. Okay? So ties and then columns. So their method of designing is rather similar, or basically they are the same. It is just that ties are only used for columns and stirrups are used for beams. So they only differ in nomenclature. So yung sa pangalan lang po sila nagkaiba. Okay. So proceeding, how can we now solve for the design, or how can we now design the shear reinforcement of a particular reinforced concrete section? So this is now the design principle according to USD, or according to ultimate strength design. And that is now VU must be less than or equal to VVN. So I think you're already familiar with this term since we have already designed a beam in terms of its bending stress. So di po ba dati? So before, you have solved for MU is equal to VMN. So this time, instead of making use of M, we would now be making use of V. So we would now be making use of V, meaning shear. Okay, so proceeding. So for VU, this is now the ultimate shear load. So this is now the demand of the required strength. And this must be following the load combination according to strength. So it is either 1.2 dead load plus 1.6 live load, or 1.4 dead load, or etc. So it must be factored. Okay, so when we say P, this is now the reduction factor. So previously for bending beams, we have solved for tension controlled, for compression controlled, or even for transition zone for the values of P. But this time, for the shear design, we only have one phi. Okay? So in shear design, our phi is now equal to 0.75. So you no need to check if it is tension controlled or compression controlled. Phi is automatically equal to 0.75 in shear design. And when we say Vn, so N stands for nominal shear strength. And we have a formula here for the nominal shear strength, and that is now equal to Vc plus Vs. So what is Vc? Vc is the nominal shear strength for concrete, and Vs is the nominal shear strength for reinforcement. Okay, so further on that, so let me just go to the code provision itself. So for shear, that is Vn. Vn shall be calculated in accordance to section 422.5. We would be going there later on. And it is said here that Vn shall be calculated by, so Vn is now equal to Vc plus Vs. So whereas Vc, that is now the strength of concrete, and Vs, that is now the strength of the steel. Okay, so looking at this figure here, suppose that it is now subject to a shear stress or a shear load. So suppose that this is now our shear load. So this shear load here is actually carried by both the concrete and the stirrups. So as you can see here, for PVC, this gray area here is the effective area for concrete that is actually contributing to the strength of shear. So this one here. And as for PVS, as you can see here guys, that we now have two lines, which is this line and this line. Which are these lines here. So this line and this line. So in shear stirrups, we have this term called legs. When we say legs, that is now the part of the shear reinforcement that actually helps in, let's say, withstanding the shear force itself. So in this case, this leg right here, so I hope that it is seen in the video. So this side leg right here, so this is actually called a leg. And this one here is actually called a leg. So in this particular figure, we have two legs. So what about this and this? So actually, if our shear force is located here, according to our computation, it is assumed that, let me just erase this. So it is assumed that this leg here and this leg here does not even help in withstanding this particular shear. Unless, of course, for example, that our shear is now located in this direction or is now oriented in this direction. This time, we would now only consider this part of our stirrups and this part our stirrup as our legs. But coincidentally speaking, we still have two legs. But in a situation we're in, for example, that, let me erase everything. So in a situation we're in that instead of us having just these stirrups here, for example, that we would be adding another stirrup here. And let's say another stirrup here, then let's say another stirrup here. If our shear force would now be oriented in this manner, we now have 1, 2, 3, 4, and 5 legs. Okay? 5 legs. But as you can see, if let's say our shear force is this one here, we only have 2 legs. Oops, sorry. So namely, sorry, let me just bring back the shear reinforcement a while ago. So even though that we have these legs here, but if our shear is oriented in this manner or vertically, it means we only have 2 legs. I hope that is clear. So we now have 2 legs. Okay, so let me just erase everything once again. So again, from our equation, VU is equal to PVN. But according to Vn is actually the combination of Vc plus Vs. And substituting equation 2 to equation 1, Vu is now equal to phi times Vc plus Vs. And substituting the value of phi, Vu is now equal to phi Vc plus phi Vs. Thus, looking at this situation here, Vu, so once again, Vu is now equal to phi Vc plus phi Vs. Okay, so moving forward. So actually, this is basically the equation that I have shown you a while ago. And we also have a limit here, whereas the value of Vu must be less than or equal to phi Vc plus 0.67 square root of f prime CBWD. So this is just a limit, guys. So as you can see that in our situation here, so again, Vu must be less than or equal to phi Vn. And if you would now be substituting this equation to this equation, Vu is now less than or equal to phi Vc plus Vs, correct? But since in this in this equation here, it is said that this is actually the limit. So limit. Meaning, guys, since as you can see, this is Vc, this is Vc, this is Vs, and does that say that this is also Vs? So yes, actually, but this is only the limit. So this is what you would be calling the maximum Vs. Okay, so there. Okay, so moving forward, how can we now solve for Vs? So actually, what we would want to do, guys, so suppose that we have a particular Vu. So in our design, we should solve for Vs in order for us to know how much shear the steel should be carrying, and basing it from that, we will now check for the spacing. So in the design of shear reinforcement, we are actually particular with the spacing. So meaning, guys, going back here, ang dinidesign po talaga natin is their spacing in order for it to withstand the shear force or the shear stress. So going back to our situation here, so as you can see that they are spaced with one another. So that is actually our main concern for this particular video. Okay. So, again, from this particular figure, VU, you should already know that from your mechanics of deformable bodies. For your PVC, guys, for the PVC, VC actually has plenty of equations to choose from. So I will be showing that to you in a short while. So again, you should already know VU. Then for the value of VC, isa-solve nyo po yan. So you would be solving for the value of VC. And upon solving for the value of VC, using this equation here, you will now be solving for the value of VS. Then from the value of VS, that is now our basis for the spacing. So again, spacing is our main concern here. And as you can see, that in this particular equation, Vs is equal to AVFYD divided by S. We are actually solving for the value of S. So, okay. So what is AV? When we say AV, guys, this is the area of legs. So that is now pi over 4 times the diameter of stirrup squared times the number of legs. Okay. So what about for FYT? So what is FYT in the first place? When we say FYT, this is the yield stress of the transverse section or the transverse stirrups, I should say. The transverse reinforcement. And for D, that is depth. And VS is, of course, the required shear strength of the steel. Okay, so again, we are actually particular with the value of S here. And from that equation, we can now say, so cross multiplying S is actually equal to AV FYT times D divided by VS. Okay, so again, we are now particular with the spacing. But our spacing also has limits. So for the limits of the spacing, we have S max here. So this is now maximum S. And it is actually dependent upon what the value of VS here. So I would be showing that to you in a short while or how to use that in our sample problem. But before that, guys, so suppose that we have a particular beam. So let me go back to this particular slide. So as you can see, guys, that in this particular shear diagram, the highest shear is actually located at the support itself. Okay? So as you can see here that the shear stress or the highest shear is on the support itself. However, according to studies, looking at the figure on the right, the failure did not actually happen at the supports. Rather, it happened a distance from the face of the support. Okay? So, let me erase this first. So as you can see that it did not happen at the support. Rather, it happened at a distance from the support. And let us say that this is now the average area of our failure. And according to experiments, for non-pre-stressed beams, this is actually at a distance D from the support. So sir, what is D? D is basically the effective depth of concrete. So suppose that this is now your concrete. So this is now the effective depth. So if that is D, this is also D. So this is equivalent to this value. So from that, guys, let me just go to this slide here. So we have a provision on where you would be getting the shear force that you would be using for your design. So according to this provision by NSCP and by ACI, for beams built integrally with support, so meaning that they were poured at the same time, VU at the support shall be permitted to be calculated at the face of support, meaning that the VU that you will be analyzing should be at this particular section, which is at the face of the support. So that is according to this particular provision. However, we have a second provision. Okay? So in this particular provision or in this provision, so it is stated here that sections between the face of support and the critical section located D from the face of support for non-pre-stressed beams shall be permitted to be designed for VU at that critical section if all of the following conditions are satisfied. So A, if support reaction in the direction of the shear introduces compression into the end region of the beam, loads are applied at or near the top surface of the beam, and no concentrated loads occurs between the face of support and the critical section. So let me just explain this. So according to this particular provision, nakadaming particular na ako today. So in this provision here for 09.3.2, it is stated here that from the face of support, let's say that we would be getting a distance d. The critical section is actually here. So meaning guys, that is now the value for your VU. But take note guys, that this provision, so this D here, so let me just get my laser pointer. So this D here is only applicable for non-pre-stressed beams. Okay? But for pre-stressed beams, that is now H over 2. Anyway, so again, we would now be getting the value of D, or the effective depth of your beam, and get its distance from the face of the column. So in here. And we can only make use of this provision if and only if A, the support reaction in the direction of shear introduces compression into end region of the beam. So what does that mean? So suppose that this is your beam, or the side of your beam, and let's say that this is now your support reaction, and let's say that we have uniformly distributed loads here. So at the end region of the beam, so let's say that this is now the end region of the beam, there is actually the presence of compression. Ibig sabihin, naiipit po yan, no? So as you can see, we have a force here and we also have a force here. And with that, guys, this region is actually being compressed. In Filipino, naiipit siya, di ba? So kapag naiipit siya, or if it is compressed, then meaning that A is already satisfied. Okay, so what about for B? So for B, loads are applied at or near the top surface of the beam. So again, why did I erase our situation a while ago? So suppose that this is once again your beam, and let's say that this is now the loads. As you can see, that the load is actually at or near the top surface of the beam. So it was not applied at the bottom part. So meaning guys, for a beam like this, for example, that this is your beam, if the load is at the bottom part, then meaning we cannot make use of this provision already. Okay? And C, guys, for C, no concentrated load occurs between the face of support and critical section. Meaning that, suppose that, again, the critical section would be located here. So let's say that this is now the critical section. Let's say that that is D. So as long as there would be no point loads at this particular region, then we can now make use of this provision, stating that the critical section is at a location D. So ulitin ko lang, no, kapag meron po tayong load or point load na nandito sa area na to or nasa region na to, bawal na po natin gamitin yung second provision. So meaning ang gagamitin nyo daw na VU is yung nasa support. Okay? So let us check further on that. Anyway, so we also have a minimum required shear reinforcement, and that is now given by this equation. So we would be discussing that further down the line during our problem solving. Okay, so let me just go to this part. Okay, so in this part, guys, this is now the equations for VC, or for the shear strength of concrete. So we have two methods as per NSCP 2015 and ACI 318-14M. So again, disclaimer that in this video, we are only particular with this code. So in the latter codes, these formulas were actually updated. But anyway, since you will still be using these formulas in your board exam soon, so ituturo po natin yun. So according to ACI 318-14M, we have two methods, namely simplified method and detailed method. And from that, guys, as you can see, mas mahirap po yung detailed method. So detailed method is actually more harder actually. But ko pa pinahirapan. So anyway, so as you can see, simplified method, you only have this particular equation. But take note that these formulas here are only effective if and only if our members are without axial force. What does that mean? So for example, guys, we have this beam here. If our only load is our transverse loads, then we can make use of these equations. However, if you would now be applying compression here, we cannot make use of these equations any longer. Rather, we should now make use of this particular equation. So it is either simplified or detailed. So common misconception is that you are actually, you were, according to some, actually required to solve for both of them. However, guys, these are two different methods. So basically, you should only be choosing one. So if you want to make use of this method here, then you will be making use of this formula. If not, if it is required for you to solve for it via detailed method, then you would now be solving for it using detailed method. And this is now the VC for non-pre-stressed members with significant axial tension. So for tension, this is now, let's say that we have a particular beam. So let's say that we have a particular beam. And aside from it having transverse loads, let's say that we now have a significant axial tension. So from that, guys, we would now be making use of this equation, regardless if it is simplified or detailed. But take note, guys, that NU here is negative for tension. So in this chapter of NSCP or ACI, the sign convention would now be the opposite as what we have been using before. Okay, so in a typical step or in designing a typical shear reinforcement, these are the approach that I can show you, but I'm not saying that this is the only way. So I'm saying that you might want to check these steps if you are lost, no? Anyway, so the first thing that you should do or you can do is for you to solve for VU using load combination. When we say VU, that is the shear at the section that you are analyzing. So next up, after solving for VU, you must now solve for VC. So from that, guys, I have already shown to you what the formulas for VC are. So upon solving for VC, you can now solve for VS using this equation. VU is now equal to phi times VC plus VS. So VS is the only one unknown here. So solve for VS. Then basing it from the VS, solve for the spacing required. Then after solving for the spacing required, compare it with Smax. Then you would now be comparing with the different parts of the provisions. Okay? So let us have our sample problem here.